Okay, so next case is let's discuss UDL smaller than span. Okay, so case 3 is UDL. We had discussed UDL larger than the span. So what happens when you have a UDL smaller than span? So let us consider that the length of UDL which is crossing the span AB is this is section C. This is AB and its span length is capital L and AC is Z. Okay. And the UDL which we are trying to cross from A to B is, let us say that it is W per meter, and the length of UDL, let it be D, small d. Okay. In this case, it is moving from, let's consider left to right. Okay. Over beam AB of span L. So we are considering the case where your D is less than capital L. Okay. That is, as usual, as we have written, UDL is smaller than span. So you are what you are trying to find is you are trying to find the position of load. Okay, position of this load. How you have to position this load to get maximum shear force and bending moment at section C. Okay, this is our aim. Okay, this is what we are trying to find out. So let us first draw the ILD. Okay, ILD for let us draw the ILD for this load. Okay. So we have to show the position. So when the load, when this small d distance load is to the left of C, okay, is to the left of C or it is occupying the point AC, then you get this negative shear force diagram like this. And when it just moves to the right of C, you get a positive shear force. So that is evident from the figure Z by L and L minus Z by L. So this is A, C and D. Okay. This is negative shear force and this is positive shear force. I will also draw and keep the bending moment diagram also here itself. So this was the ILD which we derived and which we know. Okay. Now how it differs, how we can read from this diagram is what we have to learn. So Z into L minus Z by L. This is a maximum coordinate. A and B. Okay. So now looking at the ILD for shear force at C, it is evident that negative shear force, maximum negative shear force will develop when the head of the UDL, okay, this head of the UDL reaches the section. That means your load position is somehow like this. Okay. This assuming that D is less than Z. If D is equal to Z, then this load will occupy complete AC. Okay. Or if D is greater than Z, then it will just project out of A also. Okay. So we can write maximum negative shear force. Okay. Maximum negative shear force where at C. We are discussing everything at a section. Okay. This will develop when the head of the UDL reaches the section C. Okay, it does not cross. Similarly, you can guess that the maximum positive shear force at C happens when the tail of load, isn't it? When tail of UDL reaches or crosses section C. Okay, so tail has reach the section C. So it looks like this. The tail end is, that whole load has crossed C and the tail is exactly at C. Okay. Similarly, we have one more thing to find. What about maximum bending moment? In either this maximum bending moment will develop at C, okay, will develop at C when the load is, that is when the load is placed at C. അത് എങ്ങനെ place ചെയ്തിട്ടുണ്ടാവണം? That is when the load is placed at C in such a way that some part of it is to the right of C and some is to the left of C. മൊത്തം ഇതാണ് D. So you have to find out how that load should be placed so that you get a maximum bending moment. Okay, that is what that you have to derive and find out. So you will see that. So maximum bending moment will develop at C when the load is partly to the left of section C and partly to the right. Partly to the right. Okay. So we have to derive and find out actually at what position you have to place it. So what I'm going to do is I'll just use a different color and I'm going to position the load like this. Okay. This is your load which is positioned and I'm going to consider this distance as small x. So what will be this distance? That will be small d minus x. Okay. So accordingly, I can draw the ordinates here and this is the tail end and the head end is also creating an ordinate here. So I will consider this as y1, let this be y2, and at the middle of course you will have the maximum ordinate which let us consider as yc. Okay, so the distance will mark here again, this is x and this is d minus x, and from A to C this one is z. Okay. Now, let us derive it. So, let the position of load be as shown in the figure. And when you refer to the figure, can you write what is MC? What is moment at C? So, it will be equal to area, I mean, this load intensity into area of this UDL, isn't it? So, this UDL is in the shape of a it's a trapezoid or it's a polygon, isn't it? It has got 1, 2, 3, 4, 5 sides, so it's a pentagon. So we'll treat this as two trapezoids. Okay, this is one and this one is second trapezoid. So two trapezoids, when you add those areas, you get multiply by load, you get what is the area of which is the total moment under this caused by this load. So MC is given by W, okay, that is a load intensity into X into Y1 plus Y6, sum of parallel sides divided by 2 into X is the other non-parallel side, okay, then plus W into D minus X, okay, similarly height into the parallel sides Y2 plus YC whole divided by 2, okay. So adding this, now instead of adding this, actually what we are trying to find is maximum bending moment, isn't it? So for MC to be maximum, what is the condition? Maxima or minima of a function? dmc by dx, because x is the variable. You're trying to find out x, that is the position of the load, so that you get a maximum bending moment. So dmc by dmc by dx should be equal to 0. So differentiate this term with respect to x. So what you will get? 0 should be equal to w into dx by dx is 0, so is 1. So w into y1 plus yc whole divided by 2 plus w into y2 plus yc, because these are all constant, by 2 into d minus x, you have minus 1. D is constant, so minus 1 is what you will get. So you can equate y into y1 plus yc by 2 should be equal to w into y2 plus yc by 2, or simplifying, y and y will get cancelled, 2 and 2 will get cancelled, yc gets cancelled, and finally what you get is y1 should be equal to y2. This is the condition. So that means the moment at C will be maximum when the ordinates of ILD for MC at the head and tail end of the UDL are equal. Okay, so that means you can write, hence you can write moment at C will be maximum when the ordinates, okay, when the ordinates of ILD for MC, when the ordinates of ILD for MC at the head and tail end of UDL are equal. Okay, so that is the result, y1 equal to y2. Now, once you have reached this condition, you can just find out what is x. You always have to find out x, isn't it? Or a condition for x. So from similar triangles, you can just check from similar triangles. Okay, just keep looking at the figure from similar triangles in this figure. Okay, we are just trying to get some relation between x and y's. Okay, you only got a condition for y. So from similar triangles, you can just keep referring to the figure. Okay, yeah. So you will get z minus x. So this distance is z minus x. Z minus x by y1 should be equal to z divided by yc, isn't it? So I'm going to write z divided by no z minus x divided by y1 is equal to z divided by yc, or I get y1 is equal to z minus x into yc divided by z. Okay, keep it like that. Also, from this part of the triangle, this right hand side, y2 divided by yc is equal to what is this? This y2 means you need to get this distance. So that distance is nothing but L minus Z is this distance minus D minus X. Okay, L minus Z minus D minus X is this distance. And this one is from here to here, it is nothing but L minus Z. Okay, so I'm going to write that also. So I can write y2 by yc is equal to L minus Z minus D minus X divided by L minus Z. Or from this, y2 is equal to L minus Z minus D minus X into yc whole divided by L minus Z. Now, substituting and equating. Substituting and equating. That is y1 when you use this in this equation, when you substitute y1 and y2, what I get is z minus x into yc by z is equal to L minus z minus d minus x into yc, okay, divided by L minus z. So this yc and yc gets cancelled, and then rearranging uh, z minus x into L minus z is equal to z into L minus z minus d minus x. So first open this bracket and then cross multiply. So you will get Lz minus xl minus z square plus xz is equal to zl minus z square plus zd minus no plus zx. Okay. Now equating this, you have many terms which will get cancelled on either side. So this xz, zx will get cancelled, z square and z square will get cancelled, Lz and zl will get cancelled. So you will get minus xl is equal to zd, or uh, when you bring it to this side, minus xl minus zd is equal to 0, or you will get xl is equal to zd. I'm sorry, this is minus zd here, not plus. That is why I was wondering why we are not getting. So this is minus zd. Okay, minus zd. So this becomes plus. So xl equal to zd. And what is a condition you will get is x by d is equal to z by l. This is a very important result, which means you are going to position your load. Okay, that is the x in by which you will see is equal to z by l. So the proportion, the position of moving load, it is so placed that the section divides the load in the same ratio as it divides the span. Okay, z by l എന്നുള്ള ratio is how the span is divided. അതേ ratio വേണം the load also should be divided and kept over section C. So this is very, very important result. So I'll just write it in words. So therefore, bending moment at any section or at a section is maximum, okay, is maximum when load is so placed, that the section divides the load in the same ratio, in the same ratio as it divides the span. Okay, as it divides the span. This is a very important result.